So I'll briefly talk on present and future energy scenarios and the environmental effects because of this mass energy generation, and what is the present status of the clean energy progress mission, right? And maybe at the end I'll be discussing one sustainable energy technology option. So before starting my actual topic, just I would like to show this definition of sustainability, right? So it's basically ability to meet current needs without compromising the ability of future generations to meet their needs, right? So nowadays this become a buzzword, right? People are talking more about sustainability, right? So whatever you are doing, right, whether it is say invention or mass production, right? So people now are questioning whether it is sustainable or not, right? So why? Because because of this large demand, right? Without proper measures, right? If we do something, right, that may affect our future generations, right? That should not happen, right? So this is the first window I would like to present whenever I give this talk, because how we became the master of the planet, right? So though along with us there are different living organism present on Earth, right? But the way the genetically we
Uh,
you know
Excuse me, Ram Sagar.
yeah, yeah.
Your slides are not changing.
Oh, now sir.
No, actually, your full view is not visible. Only the PPT is. So probably you may have to share the entire screen.
First I did that. Entire screen. Entire screen. So now?
Yeah, now
Yes.
it's fine.
Yeah. So like the way genetically we developed, right? The other living organisms are not improved, right? So that's why our species will be considered as our race will be considered as a intelligent species on Earth, right? But along with that, right? So we have these challenges, right? How do we? These are the past history. How do we get there, right? What are the problems current now? Are we facing any problems? And how do we stay there, right? So you can see the slide. How do we get there, right? Because of our intelligence, see, right? We have invented so many products, right? Which makes our life comfortable, right? And which also increased our lifespan, right? And in addition to that, we have also invented some products which are completely luxury, right? So and these all these products improved our quality of life, right? Then what is the problem, right? So because of that inventions, because of this comfortable life, comfortable lifestyle, right? And because of inventions even in medical field, right? Our lifespan got increased, right? And along with that, because of this so many luxury products, our energy requirements also got increased, right? So you can see the future demands in different sectors. For example, our population is about to reach 11 billions by 2050, and correspondingly, if you look at the GDP requirement, will increase 6 to 7 times the present value, and the production capacity also must increase 5 to 6 times, and the energy demand, right, and water demand, right, and parallel to that, the CO2 emissions will also increase. Right? So this is the main problem we are going to face, right, in future, right? So now, what is the challenge we are going to face? So in order to accommodate that steep increase in demand of all these different products, different categories, right? obviously we have to produce more, right? But what are we doing at present, right? So what we are doing, so we are taking whatever the natural resources present on Earth, right, and we are converting them into useful products, right? And at the same time, obviously, the conversion is not 100%, right? There will be some side products or waste products, pollutants. Those pollutants and waste products simply we are dumping on Earth, right? So this now, this becoming a major problem, right? So at the time of industrial revolution, people didn't thought about what are the consequences if we simply, don't treat that waste products or pollutant properly, right? Now that is becoming a major issue, right? Because of this mass production, to meet the current demands, we are producing more, and we are simply throwing this waste and pollutants on surface, right? So if you look at the conversion, on average, only 25% of these natural resources are being effectively converted into products, and the remaining 75 we are just dumping on surface in the form of waste products or pollutants, right? So in order to sustain, right, in future, right, the conversion at least must be increased to 40% as per the report given by Triol, right? So this is the main challenge we are facing at present, right? So this sustainability, right, issue can be applied to any process, any field, right? But here, I am limiting this discussion on the electricity generation. Okay, so if you look at the electricity generation statistics, right, this is the world global electricity generation, right, and the type of fuel we are using, majorly the coal we are using as a primary energy source for electricity generation, right? And the recent days, because of the green electricity generation mission, right, the power production using renewables, right, and natural gas is also getting attention, right? But nuclear, if you look at, there is no much improvement in global electricity generation by using nuclear fuel, right? So you can also see the power production statistics in India, right? So this is at present power production here. We are also using coal as a primary energy source for power production, right? But if you look at the future statistics, right? So India is also looking forward to minimize the utilization of coal in power production, and mainly we are concentrating in power production by using solar energy, right? So these are the projections based on the policies we are now implementing at present and future, right? So what happens means people are always talking about, yes, coal is not a green fuel, right? We should minimize the use of fossil fuels in power production, right? But what happens means what are the other consequences if we are completely rely on renewables, right? So these are the statistics gives us some idea. For example, if you want to produce electricity, 1,000 megawatt electricity, or if you want to utilize this capacity power plant, it an average requires annually 26 lakhs tons of coal, right, and 20 lakhs tons of oil, right? And this is the requirement of fossil fuel, right, coal and oil, right? If you're trying to get the same power capacity by using a solar thermal power plant, right, it required 20 to 50 kilometer square area to keep that solar panels, right? It is almost like a small city, right? And if you want to get the same thing by using wind fields, an average you require 50 to 150 kilometer square area, right? If you want to achieve the same thing by using biomass energy, right, you need to have a plantation in 4,000 to 6,000 kilometer square area, right? And the same thing you can get by using 200 tons of uranium, right? Or in 1.3 tons of uranium in fast breeder reactor, right? So you can observe, what are the consequences if we are completely relying on renewables, right? So this area requirement is very huge, and if you try to get the base load demand only by using renewables, right? So you may be, compromising on the area utilized, right? So obviously, to get the power in an effective manner, right? So the hybrid solution is always better, right? Or high density power sources are, can give the required power with the minimum resources, right? In terms of area or other things. So that's why, nuclear is always a better option, but there are other consequences, right? So because the fuel is not green, right? There are hazardous emissions will be there, right? But you have to handle that properly. Then nuclear can be a very good option, right? And coal also, requirement is less compared with the other renewables, right? But it has the other side effects that we are going to see maybe in future slides, right? So what is the main effect of using fossil fuels, right? So this CO2 gas is mainly emitted because, if we use the fossil fuel for power production, right, which affects the environment, right? The statistics, CO2 emission statistics, if we look at now, right? So the emission statistics are continuously increasing in the past years, right? And there is a decreasing trend in the last 2 years, right? This is mainly because of the pandemic, right? Not no, due to the effective utilization of renewables, right? At present, we are still mainly depending upon the coal or fossil energy, right? But this decreasing trend is mainly because of the pandemic, where the overall energy demand was less, right? That's why, the power production from fossil energies were also less. Right? So what happens as the greenhouse gas emissions, right, emit into atmosphere, right? So this affects. Just my intention is to show that greenhouse gas effect visually, right? I hope most of you are already know about this greenhouse gas effect on Earth's surface, right? So whatever the sun energy absorbed on Earth, right, will be radiated, right? If we have more greenhouse gases, right? So they absorb, they re-emit that radiation onto Earth's surface again, which increases the temperature of Earth's surface and atmosphere. Right? So presence of these greenhouse gases traps the heat, right, and re-emit onto the surface, which results the increase in temperature of surface, right? So you can observe here, most of the, countries are witnessing that high temperature during the summer seasons, right? These are the contours you can observe, right? Where, if you look at the past statistics, right, 17 of the top 18 warmest years are occurred since 2000, and out of that, 2016 and 2019 years are recorded as first and second warmest global years, right? Since 1880, right? So the temperature is keeps on increasing, and you can see the ill effects because of that a temperature rise, right? So we are witnessing extreme weather conditions, floods, right, and uh, drought seasons, right, and ice caps melting, right. So this are no consequences for species extinction, right, and scarcity in food, right, deforestation and all those things, right. So the probability of these events could have occurred by chance is virtually zero, because of the only our activities, right? Because of the CO2 emissions, right? Anthropogenic CO2 emissions, right? So this kind of extreme weather conditions we are witnessing, right? So knowing the intensity, right, the world, all countries in the world have realized that intensity, right, and they have joined their hands and come together to discuss this issue seriously in the year 2015, where the CAPE 221 conference was held in Paris, right? And in that, 195 countries voted to adopt the historic agreement, right? And in that agreement, what they said, with compromise and cooperation, right? So they were trying to halt warming at 2 degrees centigrade with measures to aim for 1.5 degrees centigrade by 2030. That rise in temperature, they are trying to halt at 2 degrees centigrade by the end of 21st century, right? And they are trying to take measures to halt the temperature rise 1.5 degrees centigrade by 2030, right? So in order to meet this target, right, they have decided the target level of CO2 as 450 ppm, right? And which, if we keep the CO2 concentration 450 ppm in the atmosphere, right? So the average temperature rise will be 2 degrees centigrade by the end of 21st century. Right? So you can check what is at present concentration, right? How the CO2 concentration is increasing with time. So India is also submitted this instrument, right, and joined in this Paris Agreement, right, on 147th the birth anniversary of Mahatma Gandhi, right? And accordingly, the India is deriving policies, right? Mainly we are, if you look at the some government reports, right? So India mainly venturing into solar energy from solar, right? So the important measures in this agreement are, we have to minimize the greenhouse gas emissions, right? And establish long-term goals for clean energy, right? And ramping up climate commitments, right? And some advanced countries has to develop support, extend financial support for developing nations so that they can get the energy from the green sources. People call Paris Climate Agreement as a turning point, right, in the fight against the effect of climate change. Right? So, as per the Paris agreements, many countries have derived their policies to limit the CO2 emissions so that they can keep the temperature rise only below 2 degrees centigrade by the end of 21st century, right? So based on that, International Energy Agency also just monitoring the clean energy progress, right? So because this, we have three major sectors which can emit CO2 at mass scale, right? One is power generation sector, and one is transportation, and the third one is industrial sector, right? So the progress in these three sectors, is continuously monitoring, and they're updating what is the state of each sector in order to meet that sustainable goal. Right? So I'll be discussing only the uh, updates on clean energy progress. Right? You can also check the progress on transportation sector. Right? Mainly the transportation sector, people are trying to use electric vehicles. Right? But when you try to link these two sectors, right? So electricity comes from either fossil or the green energy sources. Right? So when the entire transportation sector become electrified, right? So it needs large energy, large electricity, right? So that electricity should come from again green energy sources, right? Or that electricity should not again a reason for, or should not leads to release of large CO2s into atmosphere from the stationary sources, which are nothing but power plants, right? So if you look at the progress of clean energy sector, right? So ultimately, people are trying to decarbonizing the power sector, right? So we have four major uh, power sectors, right? Renewable energy, nuclear power plants, and natural gas-fired power plants and coal-fired power plants, right? So if you look at the progress, right, of these different sectors, so the renewable and natural gas-fired products are going in line with some standards, right? Some targets established as sustainable development scenario targets. Just I'll present what are they, what are the targets, what are those targets, and how they have established in the next slides. So if you look at the progress of these two sectors as per SDS targets, right? So they are going fine, but they need more efforts to to maintain that growth and to go in line with those targets, SDS targets. Whereas nuclear power, coal-fired power plants, and uh, calcium capture, sorry, CO2 capture and utilization, right, in power sector, they are not on track. They are not going in line with the SDS targets. Right? So you can see what is the SDS targets, right? So, so this SDS generally represents a gateway to the outcomes targeted by the Paris Agreement. Right? So they simply just they are monitoring how the each sector is progressing in order to meet this 2 degrees centigrade temperature rise scenario. Right? So they show the projections. They show the projections. Each sector now has to go in this profile in order to meet the 2 degrees centigrade and what is the present state. They will compare with the ideal curve and the original state. They'll compare with the ideal curve and they say whether it is following, whether the sector is on track or not. Right? So mainly this SDS scenarios, the whatever the policies they have developed, they are on track with the SDGs, right? So these sustainable development goals are proposed by United Nations long back in different sectors, and power is one of them, right? So as per this scenarios, right, and projections, I know it is noticed that advanced economic countries reach net zero emissions by 2050, and China reaches net zero emission about by 2060, and other countries can reach net zero emissions by 2070 at the earliest, right? So without assuming any negative emissions means we are not uh, capturing CO2 from atmosphere, right? No net captured CO2 from atmosphere. So without assuming this negative emissions, right? So this whatever the SDS scenario presented, that is consistent with the limiting global temperature rise to 1.65 degrees centigrade, right? With 50% probability, and after 2070 the temperature rise could be reduced to 1.5, right? So these are the different profiles, right? The track of clean energy progress. So you can see the renewables are going ahead with the SDS target, right? So but more efforts are needed for this. Whereas when you look at the nuclear, so these are the actual projections, right? Based on the present condition, right? This could be the projections depending upon the existing policies and future policies decided. But the SDS target is this. So we have huge difference between the projection and the scenario as per the SDS scenario, right? In order to halt the temperature increase 2 degrees centigrade by 2100. So the nuclear capacity or the power production from nuclear capacity, nuclear power plants should increase like this. But as per the present policies, the future projections are like this, right? So with plant constructions, the projections can be like this, right? So that's why the nuclear power production, right, is not at all on track as per these SDS targets. And you can see the coal, right? So the coal supposed to be, the production from power production from coal is supposed to be in this fashion, right? And this is not going in this way. So if you look at the previous uh, already completed year projections or utilization, so the power production from coal is continuously increasing, right? But the SDS target, as per the SDS target, so after 2019 at least, it should follow this trend, which is not possible, right? So it cannot now have a downtrend, right, from the next year onwards. As you can look at the previous year projections, the power production by using coal is continuously increasing, right? So, and the gas, yes, it has the increasing trend, right? And the STS targets also showing some increasing trend up to 2030, 35, then slowly decreasing trends. Right? So that's why it is in line with the uh, SDS targets, right? But no, to sustain this profile, right, more efforts are needed, right? Capacity must increase for some time. After that, we have to look for other options, right, to decrease the power production from this source, right? So non-fossil energy means it's again the same profile, renewable energy, right? It is showing increasing trend, but more efforts are needed to maintain this steep increase, right, in future years as well. Right. So if these sectors follow the profile derived by the based on the SDS scenario, right? So we can achieve that target, right, which is 2-degree temperature rise by end of 21st century. So CCUs, right? This also what is the effect of CCUs, right, and how the progress of CCUs in power sector, right? So this is also not in track, right? At present, only two commercial CCU units are integrated with power plant, right, where capture and utilization is happening. So one is in USA and one is in Canada, right? But there are other units, right, which are on pipeline and development stage. Right? So this is the progress of CCU, right? And as per SDS target, so this is the earlier existing profile, right, up to 2019 or 18, right? So the utilization capacity is very less, right? So but the SDS shows the projection like this, so it has to follow this path, right? But as per the developments and existing policies, so the expected profile is something like this. So that's why the CCUs are said it is not in track with SDS targets, right? So more efforts are needed to integrate the carbon capture and utilization plants with fossil sources, because we witnessed, right? So fossil energy will be continuously utilized. It cannot become zero, right? And renewables cannot meet the base energy demands in all seasons, right? So we have to look at the hybrid solution, right? And whenever we are utilizing fossil energy, right, it has to be integrated with CO2 capture and utilization systems, so that the net emissions even by using fossil energies will also be minimized. Right? So first primary thing is we have to minimize the utilization of fossil energy. If at all utilized, it has to be utilized with CO2 utilization, sorry, capture and utilization plants, right? So that is the importance of CO2 capture and utilization, right? Uh, and look at the intensity of that situation, right? So different research in different areas are going on, right? And these are the major outcomes where the CO2 capture is effectively implemented, right? We have one plant at Texas where they have used this Salem cycle, right, to capture CO2 and use CO2 as a working fluid in supercritical CO2 power plant, right? And there's one technology where fuel cell is used to capture the CO2, right? And one project is a project in Japan, right, testing CO2 capture from 166 megawatt integrated gasification combined cycle power plant. Right? And this Traxys Bioenergy also explored the option of capturing CO2 from biomass. Right? So overall, in order to manage the CO2 emissions, right? So we can use the different options, right? So first is use the alternative energy sources, right? So that fossil energy utilization can be minimized, and there is no question of CO2 uh, emission problems, right? And but on other side, right, this alternate energy sources cannot be the only sources to meet the current demand, right? So it has to go with coal, energy from fossil fuels, right? So they can supplement, but they cannot solely support the base energy demand, right? So whenever we are using the fossil energy, right, we have to use the carbon dioxide capture and sequestration technologies so that the emissions can be minimized, right? So the other option could be, improve the process efficiencies, right? Because in industries, right, most of the processes requires energy, right, which may be direct electrical energy or heat energy, right? So these forms of energies ultimately we are supplying by using the fossil fuels or renewables, right? So if you increase the efficiency of the process, right, the energy utilization will be minimized, right? So this is also a main area, right? By concentrating this, you can indirectly minimize the emissions, CO2 emissions, right? So as we are talking about, renewables are the promising options, right, to curb the CO2 emissions, right? And the progress, right, the energy generation by using the renewables are continuously increasing, right? And as per the same trend, right? So if we see the future projections, right, so they are going to meet the SDGs targets, right? But only thing is, the consistent efforts are needed. And among the renewables, if you look at, so major sources are hydropower, onshore wind, right, and solar power, right, and in future bioenergy also plays a significant role, right? So the if you look at the progress of energy from biomass, right, or bioenergy, right? So this is as per the SDGs targets, right? So we noticed a 5% increase in bioenergy in 2019, right? And right, so this is just below the 6% annual rate, which is required by 2020 to reach the STS levels, right? And there are other options, like because of urbanization, we are generating a lot of biomass, right? So there are now options are explored to utilize that municipal biomass also for power production, right? And other option is like mixed feed, So coal and biomass, combined power generation, right? Where coal utilization or fossil fuel utilization will be reduced, right? So this is the just biomass utilization, right, and production, right? This is on track, and the main advantage of biomass energy from biomass, right? So all renewables, solar PV or wind energy, whatever you say, so they are generally considered as carbon neutral because they don't use fossil fuels, and at the same time they don't release any CO2, right, at the operational level, right? So and if you look at the fossil energy from coal, gas and oil, right, so they use fossil fuels and they release CO2 into atmosphere, so they are carbon positive technologies, and renewables are carbon neutral, right? So the only attractive option with the biomass, right, so this technology can be carbon negative. What do you mean by carbon negative? That means we are removing CO2 from atmosphere, right? So this is called as carbon negative. How can it be a carbon negative? See, plants and this plants utilizes CO2 which is available in atmosphere, right? And we are using this biomass for power production, right? And if we integrate this biomass power plants with CO2 capture and utilization, right? So we will not release this CO2 into atmosphere, right? So if you look at the overall cycle, we are capturing CO2 from atmosphere, right? So that makes this biomass energy from biomass as a carbon negative technology, right? So this is becoming very attractive, right? And economic option, right, to explore, right, or to go with this that 2 degrees centigrade target, right? And if you look at the targets on CO2 emissions, right, uh, as per the 2 degrees scenario by 2050, right? So we should be able to reduce the greenhouse gas emissions, right, by in different sectors by using different technologies, right? So no doubt in power, by using renewables, we should arrest the uh, CO2 emissions in a larger way, right? And followed by CCS, carbon capture and sequestration, right? Whether you are using coal or biomass, right? If you capture the CO2 released, right? So you can arrest the emissions, and nuclear is also a potential option, right? So this is about the power sector, and all other sectors, right? If you look at, right, so this is playing a major role. The bar highlighted with orange color, right? So which represents energy efficiency, right? So by increasing the energy efficiency, you should be able to reduce the CO2 emissions, which are which is indirectly, we are consuming less energy, right? And the corresponding CO2 emissions will also be reduced, right? So transportation sector also, by increasing the efficiency, right, you can minimize the emissions. And fuel switching, this could be electric, right, and use of renewables in transportation sector, right? So as a chemical engineer, right, we have major role to play, right, in this sector, right? So in addition to other areas, right, where we can improve the process performance and reduce the energy consumption, right? And if you look at except this CCS, right, all other areas, right, are more or less it's a preventive measures, right? So we are not at all utilizing more energy by increasing the efficiency, energy efficiency. So there is no question of CO2 emission, right? Which has to be handled later on, right? So now, based on this discussion, right, uh, I would like to show one energy technology, right, which can be a sustainable option, right, if we integrated with the proper CO2 capture and utilization option. Right? So in that, I'll be discussing the calcium looping system, right, which can be effectively utilized as a CO2 sequestration option, right, and can be effectively integrated to coal or biomass-fired power plants, so that CO2 emissions can be reduced. So in this work, I'm showing the integration of this calcium looping system with biomass power plant, right? Because that can be a attractive carbon negative technology, right? So why calcium looping? So it shows less efficiency penalty compared to other CO2 capture technologies, right? And the integration of this calcium looping technology with existing power plants is very easy, right? Not much retrofittation is required, right? And one more thing is, since we are using calcium carbonate as a sorbent, calcium oxide as a sorbent, which is widely available on Earth's surface, right? And it can get in very low price, right? And effectively utilized for the CO2 capture, right? So especially India and China has a lot of potential to adopt this calcium looping system integrate and can be integrated with power plant, because we have lot of reservoirs, calcium reservoirs, right? So, and in this, the advantages of integration of this calcium looping technology, right, with biomass power plant, I am demonstrating by doing energy and exergy analysis, right? So energy analysis generally we do based on the first law of thermodynamics, right? So which tells us the quantities only, right? How much quantity of energy we are handling and what are they, right? But now people suggest along with energy you should also do the exergy analysis, because this exergy analysis will gives us qualitative assessment, right? So where we have more potential for improvement, right? Where we have more, energy destruction is happening, right? So these things will be, detailed out only if we do the exergy analysis, right? So that's why, it is always recommended to carry out energy and exergy analysis together in order to improve the process performance. Right. So this is the typical schematic view of CO2 capture process by using calcium looping. In conventional calcium looping, right? So we have two reactors, carbonator and calciner. So the calcium sorbent runs in this loop, right? So the main problem with this conventional calcium looping system is, so it is somewhat expensive, because we use air separation unit here, right, to avoid the again formation of CO2, right? We required the air separation unit, and we use only pure oxygen in calciner, right? So where whatever uh, the reaction happens, right? So that doesn't affect, or that doesn't typically needs again the separation of CO2 from nitrogen, etc. Because so here we are using the coal, right? In calciner we need to use coal, right? So if we use air here, right? So nitrogen will present, and again you have to separate whatever the combustion, because of the combustion, whatever the CO2 release, that also contains nitrogen, right? Again, separation is required in order to avoid that, right? In this already CaCO3 will be decomposed into CaO plus CO2. That CO2 is coming out, right? And it needs some energy which we are supplying by combusting coal, right? So in order to avoid the nitrogen presence in this, right, because CO2 is coming out from this unit, so we are using only O2, right? Whatever the combustion happens, that happens only because of reaction between coal and oxygen, and the resulting CO2 also we are capturing, right? And we are removing it as a pure stream, and we are storing or sequestrating, right? So because of that, we need ASU unit, right? So this requires a lot of energy, right? And efficiency of process goes down with the utilization of this conventional capture unit. This is the main deficiency with the conventional capture unit. Right? Yeah, so this is the reaction. Equilibrium reaction generally happens in the capture process, right? And by adjusting the temperatures in calciner and carbonator, we control or we control the forward reaction rate and backward reaction rate. Okay. So the literature gap what we identified are the use of air suppression unit, right, which makes the efficiency of calcium looping process slow, right, and there are no integration of these calcium looping units with the biomass power plants, right, which makes the production from biomass power plant, power production from biomass power plant as carbon negative technology, right? So because of based on these research gaps, we have taken up this problem, right? And these are the proposed objectives, right? So we coupled biomass power generation power plant with calcium tubing technology, which can be effective option for agronomic areas in India. Right? So biomass power plants generally considered as low capacity power plants. So we can establish grid independent power plants in rural areas, right? And there, biomass can be a potential option for as a fuel. Right? So we also did this thermodynamic study to evaluate the performance of the proposed configuration. So the methodology adapted, right? We did this as we basically did a simulation study, right? So we first simulated this coal-fired and organic Rankine cycle for plants, right? From the literature, right? Then the coal feed, right, in combustor is replaced with biomass, and the power production capacity is also adjusted accordingly. Right? Then these two cycles are integrated, right? The combustion cycle, right, and as well as the organic Rankine cycle are integrated by using thermal oil as a heat transfer medium. Because in organic Rankine cycle, right, we use refrigerants, right, which cannot withstand very high temperatures, right? So we need some basic heat transfer, third heat transfer fluid, right, which can transfer heat from that combustion cycle, right, from biomass combustion chamber to this organic uh, fluid, right? So to avoid that conventional ASU unit in conventional CO2 calcium looping capture system, right? So we use this double calcium looping CO2 capture system where separate ASU unit is not required. Right? So we validated this double calcium looping model with the literature, right, and integrated this double calcium looping system, right, and compared the performance of this conventional as well as double calcium looping plant. So these are the assumptions considered, right? So the pressure drop in pipes were neglected. Energy loss is considered as 1.5% of input fuel, right? And auxiliary power consumption is considered to be 5% of the gross power output. Right? So this is the composition of biomass considered in the study, and these are the some technical specifications mentioned in biomass 5 power plant. So in order to do Exergy study, right, the ambient temperature reference we have considered as 33 degrees centigrade, and in combustion 20% of excess air is used, right, and the working fluid in organic Rankine cycle considered as or 245 FA, right. So this is the uh, organic Rankine cycle flow sheet, right? So here uh, the heat basically transferred by using thermal oil in this evaporator to the organic fluid, right? So this high pressure organic fluid takes heat and evaporated, and that will be sent to turbine for power generation, then followed by condenser, then again pump, right? So the organic fluid runs in a cycle in this fashion, right? So we validated the simulated organics Rankine cycle with the literature, and uh, we were able to match the performance of the simulated organic Rankine cycle exactly with the uh, existing organic Rankine cycle performance available in the literature. Then we simulated the uh, biomass power plant, conventional biomass power plant, right? So without CO2 capture, right? So here we integrated this biomass combustor with the organic Rankine cycle by using this thermal oil tank, right? So this is the Aspin plus flow sheet, right? So where we divided this flow sheet into two sections, right? And one is combustion and one is ORC cycle, right? And we exchange the data between the two sections, right, by using the connecting streams, right? So this is the first one. Combustion biomass combustion section, where we use a Gibbs reactor as a combustion reactor, right? And yeah, biomass it's not a conventional uh, uh, product, right? So it doesn't have a specific structure. So what we did, we converted this biomass composition into elemental forms, right? Carbon, hydrogen, and whatever the other elements present. Then those elements and the corresponding compositions will be used in combustion chamber, right? And combusted by using air. So this is the simulation Aspin plus window for ORC cycle, right? So this is the heat exchanger, right, where uh, the thermal oil, right, exchange heat with the flue gases coming out from the combustion chamber, right? So this is the thermal oil exchange heat with the flue gases coming out. So this thermal oil again transferred that heat to organic Rankine cycle, organic fluid in this evaporator, right? So this is how we simulated this organic Rankine cycle, and this is the turbine used for power production, right? So that is a conventional biomass power production plant where we have not used any calcium looping system, right? So whatever the flue gases are uh, coming out from the biomass combustion, right, after heat exchanger, if heat exchange, we simply leave it to atmosphere. Whereas this is the double calcium looping system, right? So where we have again calciner and carbonator, right? So in carbonator, basically this reaction happens. CaO plus CO2 gives rise to CaCO2. Right? So the flue gases, the CO2 will be captured, right, by using the adsorbent CaO. Right? So in calciner, CaCO3 will be decomposed into CaO plus CO2. Right? So so there are now why we are calling this as a double calcium looping. So we have two calcium loops here, right? So one calcium loop is between this carbonator and calciner, right? So one calcium loop is between this carbonator and calciner, right? Where whatever the CaO is used, right, is for CO2 capture, right, in carbonator, and that will be again released, right, in calciner, right? The whatever the CO2 comes will be, you know, transferred and sequestrated later on, right? And one more loop we have, which runs one more calcium loop runs. Maybe I can say this between combustor and this calciner. Right? So this indirect loop is only utilized for energy transfer to calciner. So whatever the CaO we are using here now will be used only for will be used as energy transfer medium. Right? So in this way, right, the conventional the requirement of air separation unit in conventional calcium looping scheme is eliminated. So whatever the heat required in calciner, right, is supplied by transferring the required heat to CaO in the combustor, and again sending back here, right? So the same double calcium looping scheme is implemented in Aspin Plus, right? Integrated with organic Rankine cycle, right? So now biomass is combusted here, right? So that energy is used in calciner, right? And the remaining energy from the flue gas is also used uh, uh, in this to transfer the remaining energy from the flue gas is transferred to this thermal oil, right? And from thermal oil, the energy is ultimately transferred to organic fluid, and the power production happen. Right? So now this combustor, supplying heat to two sections. One is to calciner, right, and the remaining energy, right, from the flue gases, the remaining energy is supplied to thermal oil tank. Right? So with this integration, we were able to uh, achieve the power production as well as CO2 capture. Right? So this is a hierarchy followed in Aspin. Right? We have separate section for combustion, separate section for calcium looping, and ORC cycle. Right? So this combustion is same as what we have done in the previous conventional, similar to the conventional calcium looping. And this is the calcium integrated power plant where we have calciner and carbonator, right? And flue gases are coming from the combustion hierarchy, right? And so this is the evaporator system, right? So where uh, the heat is transferred to thermal oil, right, from the different sources, right? And that ultimately transferred to organic Rankine cycle and used for power production. Right? So these are the equations generally used for assessing the performance of that power plant. Right? Mass balance, energy balance, and network is calculated based on this formula. Right? Gross minus work required for compressor, pump, and auxiliary work requirement, efficiency, specific CO2 emissions, right? So amount of CO2 released, per unit amount of power produced. CO2 capture efficiency also calculated, total amount of CO2 capture divided by amount of CO2 capture divided by total amount of CO2 released in the plant. Right. So this is the comparison, right? So this is without calcium looping. That means conventional biomass fired power plant. So this is with CO2 capture, right? So this is with CO2 capture using double calcium looping, right? So you can see the same for the same input power, right? For the same heat input from the biomass combustion. That means the amount of fuel used is same, right? So you can see the gross power output and net power outputs, right? So these are the gross and net power outputs, right? And the efficiencies also you can compare, right? So only we have efficiency penalty of 0.1%, right, with the CO2 capture, right? So you can look at this CO2 capture efficiency parameter, right? The conventional biomass power plant doesn't have any CO2 capture efficiency, whereas with calcium looping we were able to get 90% CO2 capture. And because of this integration, the efficient the if power efficiency penalty is only 0.1%. Right. So from this analysis, you can see this is very effective, right, in the form of arresting the CO2 emissions, right? About 90% of CO2 is being captured and has only 0.1% penalty, right, in power production compared with the conventional biomass power production, right? So this is worth exploring option, right? But only thing is this, since being it a biomass fired power plant integrated with organic Rankine cycle, the capacity will be very, very low, right? So you can visualize that by using power output numbers, right? So these are the basic conclusions, right? We evaluated this thermodynamic performance, right, and we observed only 0.1% efficiency penalty, but 90% of CO2 is being captured, right? So since the results are consistent because the two simulations were done on the same system, right? Whatever the problems will be there for conventional power plant, the same problems are going to be retained in cal integrated power plant as well, right? But we are not denying it because we did only simulation study, right? Experimental investigation always gives some more details, right, and facts, right, related to this integration. And if you look at the previous flow sheet, yeah. So CO2 lean flue gas and the concentrated CO2 flue gas, right? It is just coming out at the atmospheric conditions, right? So we are not handling that to a sequestration condition, right? So if we are utilizing that at atmospheric condition, that is well and good. But otherwise, that CO2 at normal atmospheric pressure, if you directly store that, you need large volumes, right? So whenever we are handling that CO2, right, if it is only need to be sequestrated, right, it has to be compressed to very high pressure, right? So whatever the CO2 is coming out from the calcium looping integrated power plant has to be sequestrated. So for that, you need a compression train, right, which can increase the CO2 pressure to very high value, maybe 100 bar, something like that, so that it can be stored in high pressure containers at low value, right? So that was missing in earlier study. So we have integrated that compression unit as well, and after that we did Exergy analysis as well. Because as I said, that energy analysis only quantitatively tells us how much amount of energy available, etc., etc. But Exergy analysis gives us what is the actual efficiency of that unit, right? So Exergy, by definition, it gives us what is the quality of work, means how much amount of energy is practically can be utilized, right? So if you look at the Exergy efficiency of individual units, because these are all the units, combustor, calciner, carbonator, and evaporator, right? We have condenser, pump, turbine, etc. So Exergy analysis of all units, the turbine and pump have very high Exergy efficiency, and you can concentrate on the units where the Exergy efficiency is very low. One is evaporator, right? And combustor, calciner, and carbonator, and air compressor as well, right? So one more point, what you have to remember here is, like, though some units, may be having low Exergy penalty, right? But you have to see, for example, 1% increase in Exergy efficiency, right? So in this unit, right, how much improvement will be there in overall process efficiency. At the same time, 1% increase in Exergy efficiency in this unit, how much improvement will be there in overall plant efficiency, right? Because though, for example, take this. So though this has low Exergy efficiency, if the amount of energy handled here is, if it is very, very low, right? Even if you increase this to 70%, in overall process efficiency may not increase much. Whereas combustor and calciner carbonator, we are handling large amount of energy, bulk volumes. Even 1% increase in this unit, right, may result a better overall efficiency in process wise, right? So you have to see which unit needs to be targeted and what are the options available, right? Obviously, from this diagram, it is suggested to go ahead first evaporator, then carbonator, calciner, combustor, air compressor, right? So uh, based on this, if you wanted to improve design of units, right, where the efficiency, energy efficiency of the that unit, if it is increased, right, that will help us to improve the process performance, overall process performance, right? So evaporator is, it's just a heat exchanger, right? And why, I was surprised to see a lot of energy, less energy efficiency in evaporator, Exergy efficiency in evaporator, which is nothing but more Exergy destruction. Why more Exergy destruction is happening in evaporator? You can observe, because whatever the flue gases are coming and other gases, they are coming at very high temperature, right? And the same energy you are transferring to thermal oil, right? And the thermal oil will be ultimately, you will be utilized thermal oil, right, in such a amount. The thermal oil maximum temperature can go up to 400 or 450, something like that. Why? Because the organic fluid, right, does not support temperature more than that 400 or 450. Right? So this being flue gases and other streams are having high temperature, but because of the limitation here, organic fluid, which cannot be heated to very high temperature, right? So you are utilizing high grade energy, right, and you are storing in the form of low grade energy, right? So that uh, uh, difficulty, if you address, right, you may get some more better efficiency. So how can we address that difficulty? One thing is, you can look for a organic fluid, right, in the same cycle, right, which can withstand more high temperature, which can withstand at high temperature, right? So if you replace this existing organic fluid with a new one, which can go to 700, 800 degrees centigrade, right? So the evaporator efficiency can be increased, and in turn the process efficiency as well, right? So this kind of some policy decisions, right, or operational decisions, or equipment design decisions, and can definitely improve the exergy efficiency, energy efficiency, and in turn the overall process efficiency, right? So these are the just other way of presenting the data. So exergy destruction, right? How much exergy loss is there, and what is the potential we have, right? As we already saw, evaporator has very low exergy efficiency, so the destruction will be very, very high. So the 40% exergy destruction is happening here, right? And followed by we have combustor and calciner, carbonator, right? And heat exchangers. So you can see this data, and you can target the right unit to improve the overall process performance. Obviously, this evaporator has high improvement potential, right? You can straight away by changing the organic fluid, right? You can show better performance, right? So these are the formulas used to calculate the exergy efficiency and improvement potential, right? And we have also done some sensitivity study, right? How uh, the specific CO2 emission, right? Other process efficiency varies with carbonator temperature, right? Carbonator unit temperature. As we are increasing the carbonated temperature, right? So the CO2 capture efficiency is decreasing, right? So in carbonator, this is what happens, right? So this forward reaction is not favorable at high temperature. Forward reaction is not favorable at high temperature. Right? So that is what we are noticing here. As we increase the temperature, right, this forward reaction is not rate of forward. That reaction is less, so that's why the capture efficiency is decreasing, and because of that, the specific CO2 emission is increasing. Right? So based on this, you can see what is the best possible operating temperature, right, for carbonator. And we have also studied some other parameters, right? As we change the carbonator temperature, right, what is happening to uh, net efficiency, process efficiency, right? So we are not noticing any significant change in net energy and exergy efficiency as we change the carbonator temperature, right? So since there is no effectiveness in energy and efficiency as we change the carbonate temperature, but we have negative effect as we increase the carbonated temperature, that's why we decided to operate carbonator at this low possible temperature in between 630 to 640 or 50, something like that, right? And this is the amount of calcium running in a loop along with carbonated temperature, right? So this is also decreasing as we are increasing the carbonated temperature, because uh, we don't need more CaO, because the CO2 capture efficiency is low, right? Even if you use more CaO, that doesn't act as an absorbent, it is simply act as inert material and runs in a loop, right? So that's why, for a noticed for a recorded CO2 capture, right? So if you look at the required calcium running in a loop. So that also decreases with carbonated temperature. Right? So that's why the main effects are, as we increase the carbonated temperature, CO2 capture is decreasing, right? That is a negative effect. And when we look at the efficiency, the overall efficiency is slightly increasing, but not much, right? So based on these two results, we decided to operate the carbonator at this temperature range 630 to 640, right, where the requirement of CAO may be more, but we can always use the required amount of CAO, right? It is available at very low cost, right, and abundantly available material, right? We don't worry about the amount of CAO used in a loop much, right? So this analysis also gives us some idea, right, which is the most critical variable, right, and what is the decision to be taken based on the profiles, right? So these are the final conclusions. So we carried out Exergy energy analysis, right, and sensitivity studies to find out the optimal operating conditions and to check uh, which unit has more scope for improvement, performance improvement, right? So the Exergy analysis showed that the operator has more scope for improvement, and you can also take some measures to capture that possibility, right? And followed by we have combustor, carbonator, and calciner, high Exergy distractions. So you can target those units also, right, in terms of design or operating conditions, so that you can improve the process performance, right? So as we change the carbonated temperature, right, we observe that the CO2 capture is decreased. So highest capture is observed at 630, right, and the lowest is observed at 690, right? So we decided the temperature in between that 630 to 640, and this is already explained, right? So and yeah, the suitable working fluid in evaporator, right, obviously improves the performance of the calcium looping process, right? So these are the some conclusion drawn from that study, right? And moreover, if you compare uh, the conventional biomass fired power plant, right, has some efficiency, right, but with the help of calcium looping, right, we were able to capture 90% CO2, and the efficiency penalty is only 0.1%, right? Obviously, when you add the sequestration tray, right, so the efficiency penalty may increase to oh, it seems there is a problem at the end. I think at the conclusions, uh, I think my voice is got disconnected, right? And what I'm saying at the end, sir, is it audible now?
Yes, sir, it's fine. Yes.
So audible,
Yeah,
sir.
yeah. So the conventional biomass power plant, right? Though it's an attractive option, but we are not uh, capturing CO2. That is a major problem, right? If we integrate that with the calcium looping process, right, the power penalty is only 0.1%, but we were able to capture 90% of CO2, right? So in turn, if you look at uh, the overall picture, right? So we are utilizing biomass, which takes emission CO2 from atmosphere, right? And we are combusting it, and if we capture, right? So in turn, on a global scale, we are designing a technology which is a CO2 negative technology. That means net CO2 we are capturing from atmosphere, right? That can be a very attractive option in the present scenario, right? So not only stopping the anthropogenic emissions, So we have to capture CO2 from atmosphere as well to arrest this temperature rise. So in that sense, this biomass power production technology can be a very good option. Yeah. So with this, I would like to end my talk.